Well done for completing the course on acids. Hopefully you've downloaded the booklet and have answered all of the questions. These are the specification points which will be assessed in your exam. Please note you will have carried out some of these techniques in PAG number 2. Here's a recent exam question. It's multiple choice. You have on average just over 1 minute to answer each of these questions, but I think you'd probably be able to answer this one much faster than that, and there's no calculation involved. So having carried out several PAGs, you will be familiar with how to use a pipette. There's no need to force any liquid out of the pipette. It's designed to dispense exactly the volume shown on it. So you would touch the tip of the pipette onto the side of the beaker and leave the droplet in the tip. So this is clearly a much longer question. There's lots to read through, but again, it's something that you will have done in your PAG, something very similar. So the first stage is where you're making up a standard solution. So you're accurately weighing to 3 decimal places a solid. In this case, it's an acid. So you dissolve it in water, make up the solution to 250 centimetres cubed in a volumetric flask. So then you're going to carry out a titration, but clearly not with all of that solution, just going to use a portion of it, 25 centimetre cubed, which you would be measured out with a pipette. And then that's going to be titrated with sodium hydroxide solution. So there'll be a neutralisation reaction. So the first part of the question is about the colour change with the indicator. There are lots of different indicators and you're not expected to learn all of the different colour changes. It's stated in the question that the indicator is phenolphthalein and it says that it's colourless in acid and pink in alkali. So looking at the instructions, the phenolphthalein is first added to the acid that was measured out using the pipette into the conical flask. Then sodium hydroxide is added from a burette. So we're starting with acid, so the colour change will be from colourless, and then as alkali is added, at the end point it will turn pink. The next part of the question involves completing the table, which looks pretty straightforward. However, so many students, time after time, every year, lose an easy mark in this type of question. A burette has divisions of 0.1 centimetre cubed. Therefore, when reading the value on a burette, you must record to 2 decimal places to show whether the meniscus lay exactly on the line, therefore the second decimal place will be a 0, or in between 2 divisions, and so the second decimal place will be a 5. The resolution shown in the initial and final readings needs to be retained in the calculated titer values, so they should also end in a 0 or 5 and be 2 decimal places. So why do we carry out trial titrations? So it is just to estimate the titer value, which does save time. This means that in future trials you can quickly run out most of the liquid that was shown in the trial value and then just slow down to drop by drop near the end. To calculate the mean titer value, we need to use results that are concordant and disregard any others. What do we mean by concordant? Well, it's results that agree within 0.10 centimetre cubed of one another. So in this case, we can only use the titer values from runs 2 and 3, and we need to disregard the trial and run number 1. So this gives a mean titer value of 18.25 centimetre cubed. Note again, it's to 2 decimal places. You will have had practice at calculating overall percentage uncertainty in PAG activities. Each piece of equipment has its own uncertainty associated with it. So for a piece of glassware, this is usually half of one graduation. So for a burette, the graduations are 0.10 centimetre cubed. The uncertainty is half of that at 0.05 centimetre cubed. For digital equipment, such as a top pan balance, it will be half of the last decimal place. So the overall size of the percentage uncertainty is also affected by the number of measurements taken. So the more measurements that are made, the bigger the overall percentage uncertainty. The bigger the quantity being measured, the smaller the percentage uncertainty, and you can see that that is in the bottom of the expression here that I've put together. For this question, you need to remember that a burette reading is taken twice to form a titer value. You have the initial burette reading and the final burette reading, and the titer value is the difference between them. N tells us the number of repeating CH2 units in the formula of the acid. To find it, we need to know the overall molar mass of the acid, which has the unit of grams per mole. We know the mass of the acid because this was information given in the question, but we do not yet know the number of moles. This is where we use the titration information. So we know everything about the sodium hydroxide. All of that information was given. So we need to calculate the number of moles, then use the balanced equation to give the molar ratio, which will then tell us the number of moles of acid used in a titration. But then we need to remember to scale up, because remember, not all of the standard solution was used. So starting with the solution we know everything about, the sodium hydroxide, we're going to calculate its number of moles using its concentration given in the question and the mean titer value. So don't worry if you hadn't calculated the correct value for the mean titer, because the error will be carried forward. But just make sure that you convert centimetres cubed to decimetre cubed by dividing by 1,000. We can now use that number of moles of sodium hydroxide to find the number of moles of acid used in the titration. So this is where we use the balanced symbol equation, which shows an acid to alkali ratio of 1 to 2. So there are always more moles of alkali, so the number of acid moles will be half of the value previously calculated. So this next stage is one frequently missed by students in exams. So the previous answer told us how many moles of acid there were in 25 centimetre cubed. But that was only a portion of the acid that was made. The acid was dissolved to make a total volume of 250 centimetres cubed. Therefore, we need to multiply the previous answer by 10 to give the number of moles of acid in 250 centimetre cubed. Now we have all of the information needed to find the molar mass of the acid in grams per mole. And now we can find the value of N in the formula. So if we take the two COOH groups off with a total mass of 90, this leaves a value of 42 to account for all of the CH2s in the formula. For the longer version of this video and further answers, please head over to my website science123.co.uk/courses, and this video is found in the AS level course on acids.